Nuclear fusion is a nuclear reaction in which atomic nuclei of low atomic number fuse to form a heavier nucleus and release energy. For all those who don't know, lately I've been creating my own model and hoping to develop something that could create the first functioning fusion reactor that is self-sustaining. In this video, I'll talk through the problems with nuclear fusion at the moment and the reason why we don't have any nuclear fusion reactors to date. What is a fusion reactor? Fusion reactors are devices that produce electrical power from the release of energy in a nuclear fusion reaction. The energy production mechanism in a fusion reactor is in the joining of two light atomic nuclei, as I've already stated. When the nuclei fuse, a small amount of mass is converted to a large amount of energy. Energy and mass are laid through Einstein's relation of E equals mc squared by the large conversions of factor c squared, where c is the speed of light, about 3 times 10 to the power of 8 meters per second. Fusion reactions are inhabited by the electro-repulsive force, called the Coulomb force, that acts between two positive charged nuclei. The two nuclei must approach each other at high speeds in order to overcome their electrical repulsion to attain sufficiently small separation, well, less than 1/1,000,000th of a centimeter to be exact, so that at short range strong force dominates. For the production of useful amounts of energy, a large number of nuclei must undergo fusion. That is to say, the gas fusing the nuclei must be produced. In a gas at extreme high temperatures, the average nucleus contains sufficient kinetic energy to undergo fusion. Heating an ordinary gas beyond temperature which electrons are knocked out of their atoms can produce such a medium. The result is an ionized gas consisting of free negative electrons and positive nuclei. This ionized gas is in a plasma state, the fourth state of matter. Most of matter in the universal plasma state is in the sun. Why don't we have nuclear fusion? Well, the volume, which is something that's been neglected over the years, plays a very large role in the power and the possible heat and energy emitted from the reactor. If we use just a simple equation, it is immediately evident that volume is something overlooked but fundamentally important. For example, if we use the equation P over V equals E fusion 1/4 of n squared subscript E brackets omega V, end of brackets, it should be instantly important, and I'll explain why. Because here I'm using P to represent power and V for the volume, and subscript E for the electron density of the plasma, omega to represent the fusion cross-section, and V relevant density, and of course E fusion to represent the emitted energy from one fusion reaction. In simple, from this equation, it's evident that the changing of V can be detrimental to the power and the output of the equation. It also shows that the volume of greater relative density means that the electron density is exponentially bigger, which equates to the energy emitted having a higher neutron electron count, so in the end we're receiving a much higher energy and heat level placed onto the wall, which can be the difference of MEV to GeV. Another equation I designed to explain the importance of volume is the following. F subscript F equals 1 over V at sigma n subscript S of the summation of Fi in the presence when I equals 1, which equals 1 over V is sigma n subscript S, Z subscript S multiplied by E of brackets E plus V subscript I multiplied by B. Here I use F subscript S to act as the force on the plasma, then using Z subscript S E and the second half of my bracket to represent the force of an individual particles due to the electromagnetic fields used by N subscript S. As a small volume, we can create an equation that shows us the force on the plasma. From looking at the equation at once, it again shows that creating a smaller volume is a greater force exerted on the plasma, which means not only do we have more control over the plasma when we start introducing magnets and the energy of the particles, it also gives us a greater confinement, which means that heavy ions can be easily removed, and so we can keep the heat necessary instead of having a deacceleration of the necessary plasma. Now, looking and keeping on my equations and looking at the importance of volume, it's evident why there is some substantial deacceleration to plasma, as we know in the Waldenstein-Sieben X at the moment, and ITER, the project that's growing at the moment. For example, ITER, the site is going to hold a fusion reactor with a plasma chamber around 30 meters. The only reason
for our biggest hope at the moment is because the power input is so great, it could create a star. Now, there are reasons why you would have such a large chamber, mainly because the more input you're able to have. But for ITER to be self-sustaining and the plasma, it either has to get a lot bigger with a greater input or a lot smaller with a similar input. I'm not now going to go into the cost of deuterium and the price of different building materials, as I want to keep this on the raw components of what really lies between why we don't have nuclear fusion. So I'm going to leave the video here, and if you liked the video, please like and subscribe, and as always, thank you for watching.